Question 10. A particle of mass 0.1 kilograms is suspended from a fixed point 0 by a light inextensible rod of length 30 centimeters. The rod is rotating in a vertical circle with diameter AB and makes an angle theta with OB. The particle has a speed of 1.2 meters per second at position A. And there's a diagram there already clear. Question A. Use a conservation of energy to find the speed of the particle at B. Level 10 part A were asked to use the conservation of energy. Now, what does the conservation of energy mean in this context? Well, we've got something that is going from point A all the way around to point B. So as it goes around, it'll get faster and faster and faster, but as it gets faster and faster and faster, it loses height. Therefore, it's losing potential energy. But there's something remains the same. At all points in that journey, something remains the same. If we calculate its kinetic energy at any given point, and we add that to its potential energy at any given point, we always get the same answer. And that's what's meant by the conservation of energy. We're not gaining energy and we're not losing energy. So in our question, the kinetic energy at point A plus the potential energy at point A must be equal to the kinetic energy and the potential energy at point B. Notice it's falling to a height of 60 centimeters. Put our values in, simplify it, and we get our answer for velocity at point B. B. Find the tension in the rod when the particle is at A and interpret your answer. So we're asked to find the tension in the rod and interpret our answer. So this is a question on forces, and if it's a question of forces, we have to use Newton's laws of motion. Second and third in this case. Newton's second law. The unbalanced force acting on a particle is equal to the mass of the particle times the acceleration of the particle or the body. But in this case, the acceleration, remember, is equal to v squared over r because we've got circular motion here. And v and r have the usual meanings. We also have to use Newton's third law here, and I'll explain where that comes in shortly. First of all, we should ask, so what's meant by the tension in the rod? Well, the tension in the rod is the force the particle exerts on the rod. It's the force the particle exerts on the rod. But however, when we're doing these questions though, we tend to focus on the body we tend to focus on is the particle. So we don't look at the forces acting on the rod, we look at the forces acting on the particle, and then we can find the force acting on the rod using Newton's third if required, and we are required to do that here. So we set it up. Newton's second law. There are two forces acting on the particle. The force on the particle is due to the gravity. That's its weight, and that's always negative, and it's always downwards. The other force acting on the particle is the force on the particle due to the rod. Now, we don't know the magnitude of that force, and we do not know its direction. That's what we're asked to work out. But we do know what they add up to. They add up to mv squared over r. And since it's going in a circle, mv squared over r has to be pointing towards the centre of that circle, and since we're at position A here, that's directly downwards. So the weight of the particle and the unbalanced force are both in the negative direction, and we can insert that in our formula right at the beginning. So then we solve it, and we get the force on the particle due to the rod. And if we get the force on the particle due to the rod, we can use Newton's third law, to get the force on the rod due to the particle, which will be the exact same magnitude but opposite in direction. And when we do that, we find ourselves the force on the rod due to the particle, which is the tension, is in the negative direction, therefore it is pushing down on the rod. The particle is pushing down on the rod, meaning the rod is being compressed. When the particle and the rod, when the particle attached to the rod was past at 1.2 meters per second, as you will see in the solution. C. Find the size of the angle theta when the tension in the rod is 0. Question C. Find the angle theta when the tension in the rod is equal to 0. So if the tension in the rod is equal to 0, the rod is no longer pushing or pulling on the particle, and the particle is no longer pushing or pulling on the rod. So there are no forces on the particle due to the rod, but it's still in a circle. Therefore, it's still accelerating. And if it's accelerating, it needs an unbalanced force, and that unbalanced force has to be towards the center of the circle, and that, of course, is equal to the component of the particle's weight towards the center. And that can only occur when the particle is at the top end of the circle. At the bottom end, the particle's weight will tend to pull it out of the circle, and you necessarily need a tension in the rod to keep it in the circle. So I've defined a new angle here measuring from the top, and I've called that angle alpha. I can always subtract this angle alpha from 180 to get back to theta, which are required to do. So to solve this question, we have to use both principles of physics, the conservation of energy, and Newton's laws of motion, to find two different expressions that we can solve simultaneously in order to get one expression with one unknown. Firstly, Newton's second law of motion, F equals ma. Now the only force acting here is the force towards the centre of the circle, and that has to be equal to mg cosine alpha. Look at the diagram. That's the only force acting towards the centre, and that has to be equal to mv squared over r. And that's as far as we can take that. That's by Newton's second law of motion. Now as the particle goes round, as it falls round, it loses potential energy and it gains kinetic energy. And it's falling through a height h. And you look at the diagram to see how that height h has been worked out, not that difficult. Put all these values into our conservation of energy principle, get another expression with v squared, eliminate v squared by solving them simultaneously, then you end up with an expression with only one variable, cosine alpha. Solve it for alpha and subtract the alpha from 180 degrees to get 146. And that's the angle drawn in this diagram where the tension in the rod is equal to 0.